So in this chapter, we learn about several different types of chemical reactions. So first, precipitation reaction, and secondly, acid-base neutralization reaction. So finally, that I want to talk about reduction oxidation reaction, and we are going to use three different definitions of oxidation and reduction. Then we also learn about how we can determine the oxidation number or oxidation state of atoms in a molecule or compounds. Then I'm going to show several examples of redox reactions, and also we want to talk about redox titration. Okay, now I want to discuss about three different definitions of oxidation and reduction reactions. As time goes on, the definitions of oxidation and reduction reactions has been expanded. Originally, the oxidation and reduction reaction was involved with the reaction with the oxygen. So when a reactant substance is combined with the oxygen atom, the reaction was defined as oxidation reaction. On the other hand, the reactant substance loses oxygen atom, the reaction can be viewed as a reduction reaction. So here is an example. When a magnesium element reacts with the oxygen molecule to produce magnesium oxide, the reactant substance doesn't have any oxygen atom, but the product contained the oxygen atom. So this reaction is apparent to the oxidation reaction, since magnesium atom was combined with the oxygen atom. Now, if we look at the second reaction, when magnesium oxide reacts with the carbon atom, it produces magnesium and carbon monoxide product. So our initial reactant contained the oxygen atom. Then as a result of reaction, the magnesium oxide lost oxygen to become original magnesium element. So this reaction can be defined as a reduction reaction. Since scientists discovered the presence of electrons in nature, the definition of oxidation and reduction reactions has been changed as well. So the new definition of oxidation reaction is when a reactant substance loses electrons, we can define the reaction as oxidation reaction. On the other hand, when reactant gains electrons, we call the reaction the reduction reaction. Let's take a look at the same chemical reaction as before. A magnesium element's reaction with the oxygen, which produces magnesium oxide. Magnesium and oxygens are elements. On the other hand, magnesium oxide is an ionic compound which consists of the magnesium 2+ cation and oxide anions. We can split these reactions into two half-cell reactions, each of which is involved with the reactant substance, magnesium and oxygen. So in the case of magnesium, it is becoming a magnesium 2+. On the other hand, oxygen molecule will turn into 2-oxide anion. Since magnesium atom it has neutral charge, on the other hand, magnesium 2+ has 2+ charge. So to balance the charge, we can place 2 electrons in the product side so that the balance was completed. On the other hand, oxygen case is that oxygen molecule is zero charge. However, oxide anion has 4 minus charge overall because we have two oxide anion. So to make it balance, if we place 4 electrons in the reactant side, then the charge is balanced. The overall balanced reaction is involved with the two magnesium atom. Um, for the haplosyl reaction, we can multiply by 2. Therefore, 2 magnesium atom is actually losing 4 electrons. Now that how do we understand this overall reaction is that 2 magnesium atom loses 4 electrons, and these 4 electrons is gained by oxygen molecule to become oxide anion, 2 oxide anion. So this oxidation reaction and reduction reaction occurs at the same time and complete the chemical reaction. So now let's learn about different definition of oxidation and reduction using oxidation states or oxidation numbers. So let me start with the definition of oxidation state. The oxidation state of an atom is defined as the charge that atom in a compound would carry if the compound was purely ionic. So in reality, the compound can be a molecular compound or an ionic compound, but we treat it as a purely ionic compound to determine the charge of an atom. So that's the definition of oxidation state or oxidation number. So now that how do we define the oxidation? So when the oxidation state of an atom shows an increase during the chemical reaction, we say that the atom in a chemical substance underwent an oxidation. On the other hand, the oxidation state of an atom in a chemical substance shows a decrease during the chemical reaction. We will say the atom underwent a reduction process. So I will give you an example how we use the definition in terms of a chemical reaction. So here we have carbon monoxide reaction with water molecule to produce CO2 and H2O. So in this case, we are just going to pay attention to carbon atoms and hydrogen atoms. And we calculated the oxidation states for these carbon and hydrogen atoms before and after the reaction was completed. So we are going to learn about how we can determine oxidation state later. We just would like to focus on the definition of oxidation and reduction at this stage now. So the oxidation state of carbon in carbon monoxide is +2, and the oxidation state of hydrogen in H2O is +1, and the oxidation state of carbon in CO2 is +4, and hydrogen in H2 shows 0 oxidation state. So apparently, in the case of carbon atom, you will be able to see the oxidation state of carbon atom was increased from +2 to +4. So this carbon atom underwent oxidation. On the other hand, in the case of hydrogen, the oxidation state of hydrogen was decreased from +1 to 0. Now we are saying this hydrogen atom underwent a reduction. Now, when you look at this chemical reaction, it is important to know that the substances that are involved in this reaction are not actually ionic compounds. So carbon monoxide, H2O, CO2 are molecular compounds, and hydrogen is molecules. So they will have covalent bonds, not ionic bonds. However, to determine the oxidation state, we assumed that these substances is actually having ionic bonding characters. So this is a very important point for you to keep in mind. Then the next question is, how do we determine the oxidation state of atoms in an ionic compound? This is relatively easy because in the case of ionic compound, the bonding character is ionic, and the charges of cation and an anion will be regarded as the oxidation states of those atoms that comprise an ionic compound. So here we want to take a look at some few chemical reactions to use the definitions of oxidation reduction that we learned before. So let's start with the sodium chloride formation, starting from sodium metallic elements and chlorine molecules. So this chemical reaction can be broken up into two half cell reactions. So one includes sodium element, and the other will include the chlorine element. And the sodium chloride consists of Na plus and Cl minus ion. Sodium chloride is an ionic compound, right? So the initial reactant is sodium, and the final product will be Na plus for one half cell reaction. Then the other half cell reaction is we start with the chlorine molecule, and the product will be 2-chloride anion. So since we have two sodium atoms, they will lose 2 electrons. If it is one, just 1 electron. And these 2 electrons are gained by chlorine molecule and produce 2-chloride anions. So since the sodium lost the electrons, it will be oxidation. On the other hand, chlorine gained 2 electrons, it will be reduction reaction. So easy way to remember is oil-rig. So that is oil oxidation includes loss of electrons, and reduction includes gain of electrons. Another terms that you guys have to remember is oxidizing agent and reducing agent. Oxidizing agent means an agent that is reduced during the chemical reaction, but oxidizes the other reactant that will be oxidizing agent. So in this case, the chlorine will belong to the oxidizing agent. The reason is that chlorine gained 2 electrons. So where does the electrons come from? Those electrons come from the sodium atoms, right? So the sodium apparently underwent oxidation reaction. So therefore, chlorine can be called oxidizing agent. On the other hand, a reducing agent is an agent that is oxidized during the chemical reaction, but reduces the other reactant that will be reducing agent. So when you pay attention to sodium, sodium underwent oxidation reaction, and where does the electrons are used? So these electrons are used to reduce the chlorine molecule, right? So therefore, the sodium can be called a reducing reagent. So it is very important to remember the definition of oxidation and reduction, and the oxidizing agent and reducing agent. Okay, now let's move on the topic of how we can determine the oxidation numbers of atom in a molecule or compound. So that is a very important topic. So now I will discuss the rules for assigning the oxidation numbers or oxidation states of atoms in a molecule or a compound. So rule number one just states that the oxidation number of an atom of the element in any elementary substance will be 0. So here we have copper, chlorine, sulfur, phosphorus. All these substances are elements, and except for copper, they all have covalent bonds between the atoms of the same element, and therefore the pairs of electrons must be equally shared between atoms of the same element. So in other words, there must be no transfer of electrons from one atom to the other atom within the same element. So the oxidation number of copper, chlorine, sulfur, phosphorus, all these are 0. All right. And the second rule is that the oxidation number of charged monatomic ion will be equal to its charges. So I mentioned this topic before, this statement, this rule before. And if we have monatomic cation or anion, its charge will be automatically its oxidation number. So we have Na plus, Mg2 plus, aluminum 3 plus. So the oxidation number for Na plus is a +1, Mg2 plus is a +2, aluminum 3 plus is the oxidation number is a +3. And so this rule also applies to the cation in an ionic compound as well. So the oxidation number of sodium in NaCl will be +1, and magnesium chloride case is +2, and aluminum chloride case, the aluminum oxidation number will be +3. So this is easy, right? Rule number 3 will be a useful rule when you need to determine the oxidation numbers of atoms that comprise a molecular compound or a polyatomic ion. So this rule states the sum of all the oxidation numbers of the atoms in a molecular polyatomic ion must equal the charge on the particle. So here the particle means is that it can be molecule or polyatomic ion. So therefore, in the case of CH4 is methane. This is a molecule, and it doesn't bear any charges. So if you add the oxidation number of carbon and the oxidation number of hydrogen together, that would be 0, because CH4 is electrically neutral molecule. On the other hand, SO42 minus, which is a sulfate anion, the overall charge is 2 minus. Therefore, if you add the oxidation numbers of all individual atoms together, it will lead to -2. Okay, so later on that I want to show how we can apply these rule number 3. Okay, basically rule number 4 states that the oxidation number of sodium, which belongs to group 1A alkali metals, is equal to +1. Group 1A elements tend to have a +1 charge when it forms an ionic compound with a non-metallic element, right? So the oxidation number of sodium in sodium chloride must be +1. Similarly, the oxidation number of potassium in potassium fluoride must be +1. Then let's try to figure out what will be the oxidation numbers of chlorine in sodium chloride and fluorine in potassium fluoride. So if you use the rule number 3, you will find that the oxidation number of chlorine in sodium chloride must be -1, and the fluorine will be -1. Why? Because the sum of the oxidation numbers of sodium and chlorine in sodium chloride must be 0. Therefore, the oxidation number of chlorine must be -1. In the same manner, you can find the oxidation number of fluorine in potassium fluoride. Rule number 5 is very similar. It states that the oxidation number of group 2A elements is +2, and you can remember that group 2A elements tend to have +2 charge when it forms an ionic compound with a non-metallic element. So the oxidation number of calcium in CCl2 must be +2. And if we apply rule number 3, the oxidation number of chlorine will be -1. So you can say that the 2 electrons from one calcium atom are transferred to 2 chlorine atoms, and each of which will receive 1 electron from one calcium atom. So rule number 6 states that the oxidation number of fluorine is typically -1. You will not be surprised that if you remember, the group 7A elements tend to form -1 charge when it forms an ionic compound with other metallic element. So if in particular fluorine element is the strongest among the halogen elements, such as fluorine, chlorine, bromine, iodine, in gaining electrons from other elements. So for example, if you consider sodium fluoride ionic compound, the sodium belongs to group 1A, so it typically has +1 charge, and the fluorine belongs to group 7A, and it is a non-metallic element, and it has -1 charge. Then how about molecular compounds such as oxygen difluoride and hydrogen fluoride? So let me start with the hydrogen fluoride case. So the oxidation number of fluorine is -1. Then how about hydrogen? We have to use the rule number 3. So the sum of oxidation numbers of atoms is supposed to be 0 in the case of molecular compound. So therefore, let's just say the oxidation number of hydrogen is X, which we would like to determine. And if we add the oxidation number of all the atoms together, which is X plus minus 1, then it is supposed to be the charge of the molecule. In this case, hydrogen fluoride molecule has 0 net charge. So this is supposed to be 0. Then the oxidation number of hydrogen will be plus 1. Then how about oxygen difluoride molecule? So fluorine is again minus 1 oxidation number. And what will be the oxidation number of oxygen? So let's put it is X. So then if we add the oxidation numbers together, so that we have oxidation number for oxygen is X, and we just have one oxygen, plus the oxidation number of fluorine is minus 1, and we have 2 fluorine atoms, so therefore multiply by 2. Then the net charge of OF2 is supposed to be 0. So then if you solve for X, you will be able to get plus 2 oxidation number. So the oxidation number of oxygen in this case supposed to be plus 2. Please keep in mind the oxidation number of oxygen is typically minus 2, but when it is combined with the fluorine atom, it will have a plus 2 oxidation number because fluorine is more electronegative and would like to gain electrons from other elements. So therefore, oxygen can lose electrons instead of gaining electrons. So rule number 7 says that the hydrogen has plus 1 oxidation number in its compound. Let's try to figure it out, the oxidation number in these cases. So we have hydrogen chloride molecule, and hydrogen probably have a plus 1 oxidation number. Then the oxidation of chlorine can be easily determined and must be minus 1. So again, we are going to use rule 3. So the oxidation number of atoms are together will lead to the net charge of the molecule. So in this case, that is a 0. Then let's figure out the oxidation number of hydrogen for CH4. So the oxidation number of hydrogen is plus 1. Then how about the oxidation number of carbon? So let's say that is X, right? Again, we are going to use the rule number 3. So the oxidation number of carbon is X. So how many carbon atom do we have? So we only have one carbon atom, plus the oxidation number of hydrogen is plus 1. And how many hydrogen atoms do we have? We have 4. So we have to multiply by 4 here. So this sum will be 0 because CH4 doesn't have any charges. It is not a polyatomic ion, right? Then if you solve for X, it must be minus 4. So the oxidation number of carbon, in this case, minus 4. But there is an exception for rule number 7. If hydrogen is combined with a metallic element, the oxidation number of hydrogen is supposed to be -1. So sodium hydride, this is ionic compound, and sodium has +1 charge, and the hydrogen, you can expect that it has -1 charge. So remember that when hydrogen is combined with a metallic element, the charge must be -1 instead of a +1. Okay, so here is the final rule. So this is the rule for the oxidation number of oxygen. Remember that oxygen in general have -2 oxidation number, but depending on the types of a molecule that we are dealing with, the the oxidation number of oxygen can vary. So in the case of sodium oxide, it is very clear that the oxygen will have a -2 oxidation number. According to rule number 4, the oxidation number of sodium is +1. And if you try to determine the oxidation number of oxygen, we can easily figure it out. That is -2 in this case. And in the case of hydrogen, I'm sorry, in the case of water, according to rule number 7, the oxidation number of hydrogen is +1. So if you try to determine the oxidation number of oxygen, in this case, that is -2. Here that I have a few examples that shows oxygen can have various oxidation number. And again, that you try to put X for the oxidation number of oxygen, and then follow the rule number 3. Then if you try to solve for the oxidation number of oxygen, as you can see here, they can have various oxidation number. Another point that I want to make out is the oxidation number even can be a fraction. So for example, in the case of KO2, the oxidation number of oxygen was -1/2. And in the case of O3 minus ion, the oxidation number of oxygen was -1/3. So you're not supposed to be surprised if you find the oxidation number in a form of a fraction, okay? So now I want to show how we can determine the oxidation numbers of atoms that comprise molecules or compounds. So here is my tips for you. If the compound is an ionic compound, it will be better to break up into a cation and an ion. So the reason is that the charge of the cation will be automatically the oxidation number for the metal. And if the anion is particularly monatomic, then the charge of that monatomic anion will become oxidation number. However, the anion is polyatomic. You have to follow rule number 3 and other rules. And also, if the compound is a molecular compound, you generally follow the rules that I have mentioned before. So I have 4 examples. Then I want to show how we can solve these questions. So in the case of KCl, this is ionic compound apparently. So potassium chloride can be broken up into K plus and Cl minus. Therefore, the charge of potassium and chloride will become their oxidation number. Therefore, the oxidation number for potassium is +1 and chlorine is -1. Then second example is potassium dichromate. So Cr2O7 is apparently polyatomic anion, and it will break up into 2 potassium and dichromate anion. The charge of potassium will become the oxidation number for potassium. And now that we have dichromate, and we have to find out the oxidation number for chromium and oxygen. According to rule number 8, the oxidation number of oxygen is -2. Then let's put the oxidation number of chromium as X. Now we finally apply the rule number 3. So if we add all the oxidation numbers together, then that will lead to the charge of dichromate anion. So in this case, that is -2. So the oxidation number of chromium is X. Then we have 2 chromium atoms plus the oxidation number of oxygen is -2, and we have 7 oxygen atoms. So that will become the charge of dichromate anion, which is -2. Then if you solve for X, you will be able to get 6. So in conclusion, the oxidation number of oxygen is -2. Then chromium supposed to be +6. The next example is a sodium nitrate. Nitrate is apparently polyatomic anion, and we can break up into Na plus and nitrate anion. So the charge of sodium will become the oxidation number for sodium. Now that we want to figure out the oxidation number of nitrogen and oxygen respectively. So we want to apply rule number 8 to determine the oxidation number of oxygen. So in that case, that is -2. And to determine the oxidation number of nitrogen, we want to put it as X. Then if we add all the oxidation numbers together, it will become the charge of a nitrate anion, which is -1. And if you solve for X, you will be able to get +5 oxidation number for nitrogen. So therefore, the answer is that the oxidation number for oxygen is -2, and the oxidation number for nitrogen is +5. So the next example is hypochlorous acid, HClO. So we can break up into H plus and Cl minus ion. So the charge of hydrogen will become its oxidation number. So that is +1. Then hypochlorous anion has -1 charge. And again, according to rule number 8, the oxidation number of oxygen is -2. And we want to determine the oxidation number of chlorine, and we can put it as X. So if we add these oxidation number together, that will be the charge of hypochlorous anion. And then if we solve for X, that will be +1. Therefore, the answer in this case is that oxygen will have a -2 oxidation number, chlorine will have +1 oxidation number. So far, we have learned about how to determine the oxidation number of atoms in a molecular compound. Now I want to show examples of reduction oxidation reaction. If the oxidation number of any atoms or elements in a molecular compound is changed, we can say the chemical reaction is a redox reaction. When the oxidation number of atoms increases during the chemical reaction, that particular substance underwent oxidation. On the other hand, that the oxidation number of atoms decreases during the chemical reaction, that particular the substance underwent reduction. So let me start with the first chemical reaction, which shows the reaction between aluminum and bromine to produce aluminum bromide. In the case of aluminum, the oxidation number is 0. Bromine is also 0 because they both belong to elements. On the other hand, the oxidation states of aluminum in aluminum bromide will be +3. So we can view the aluminum bromide as an ionic compound. Therefore, it consists of the aluminum cation and bromide anion. Therefore, the charge of aluminum is +3. Bromine is -1. Therefore, the oxidation states of aluminum is +3. Bromine will be -1. So when you pay attention to aluminum, the oxidation states has been increased from 0 to +3, which indicates that aluminum underwent oxidation because the oxidation number increased. On the other hand, when you focus on bromine, the oxidation number actually has been decreased from 0 to -1. So we can say that bromine underwent reduction. Since we learn about the definition of reducing agent and oxidizing agent, in this case, aluminum can act as a reducing agent. On the other hand, bromine acted as the oxidizing agent. Now, let's take a look at the second example. The reactant in this case is potassium chlorate. This compound was decomposed into potassium chloride and oxygen. Again, that we want to determine the oxidation number of the compounds first. So we have to follow the rules that we learned before. So in the case of the ionic compound, it will be easy to break up into cation and ions, right? So potassium chlorate cases that you can break up into potassium and chlorate and ion. After that, you can assign the oxidation number of a potassium is +1, and the oxygen is -2, and the chlorine is +5. So I don't wanna show in detail, but you guys have to make sure how to do it using the previous examples. And the potassium chloride case is that the oxidation number is +1 and -1. And in the case of oxygen molecule cases, that oxygen is elements. Therefore, if you use the first rule, the oxidation number of oxygen is supposed to be 0 in this case. Now, it is very clear that the oxidation number of chlorine has been decreased starting from +5 to -1. So we can say that chlorine underwent reduction. However, in the case of oxygen, the oxidation number was increased from -2 to 0. So we can say the oxygen atom underwent oxidation. Okay, now let's take a look at a classical chemical reaction. So this is a propane combustion reaction. And according to traditional definition of oxidation and reduction, this is apparently, we called it oxidation reaction because the carbon was combined with the oxygen atom, right? But we want to take a look at this chemical reaction using a newer definition based on oxidation number change. So let's try to determine the oxidation number first, according to the rules that we learned before. Then let's take a look at how those oxidation number has been changed. So when you take a look at C3H8, the oxidation number of hydrogen is +1. After that, using rule number 3, you will be able to determine the oxidation number of carbon is -8/3. So this is a fraction number. Then the oxidation number of oxygen in O2 molecule is 0 because it is an element. Then the oxidation number of carbon in CO2 is +4. Then oxygen must be -2. In H2O, the oxidation number of hydrogen is +1, and oxygen is -2. So now that when you look at the oxidation number change of carbon, you can see that the oxidation number has been increased from -8/3 to +4. We can say that the carbon underwent oxidation reaction. On the other hand, the oxidation number of oxygen has been decreased from 0 to -2. We can say the oxygen underwent a reduction process. Since the carbon in C3H8 underwent oxidation process, we can say that C3H8, the propane, is a reducing agent. On the other hand, oxygen could act as the oxidizing agent. So here we have two more chemical reaction, and let's determine whether these reactions belong to redox reactions or not. So the answers are actually both are the redox reactions, and let's see how the oxidation number has been changed during the chemical reaction. So first we have zinc reaction with the hydrochloric acid. And the zinc metal is actually completely dissolved, and it produces zinc chloride along with the hydrogen gases. So the oxidation number of zinc has been increased from 0 to +2. So zinc underwent oxidation. On the other hand, the hydrogen in HCl, the oxidation number has been decreased from +1 to 0. So the hydrogen was actually reduced. Therefore, we can say that zinc acted as a reducing agent, and hydrochloric acid was actually acted as a oxidizing agent. So the last chemical reaction that I want to show to you is disproportion reaction. The meaning is that an element in one oxidation state is simultaneously oxidized and reduced. So this particular chemical reaction is very useful because this reaction can actually be used as a disinfectant treatment. So if we determine the oxidation number of chlorine in chlorine molecule, it must be 0. And the oxidation number of oxygen in OH minus ion is -2, and hydrogen is +1. Then Cl minus ion, which is hypochlorous ion, the oxidation number of chlorine is +1, oxygen is -2, and the chloride ion is -1. The oxidation number of hydrogen in H2O is +1. The oxidation number of oxygen is -2. So when you look at the oxidation number of chlorine, on one hand, the oxidation number of chlorine has been decreased from 0 to -1. Apparently, chlorine atom underwent reduction. On the other hand, when you look at this chlorine, the oxidation number has been increased from 0 to +1. That means that this chlorine atom was oxidized. So when we look at this chlorine molecule, on one hand, its oxidation state has been increased. On another hand, the oxidation state was decreased, right? So this chlorine molecule actually acted in both ways. Therefore, this reaction is redox reaction, but also we call it a disproportion reaction. Yeah, so here I want to show some demo experiment. Both of them are redox reactions. So in a laboratory, you can easily conduct this type of experiment. So the first experiment is you can have a copper coin, so penny coin, and you have uh, nitric acid, so HNO3. So you add nitric acid in a test tube and place copper coin in the nitric acid. So what you can see here is that actually coin is going to react with the nitric acid, and the solution color turns into a beautiful sky blue color. And at the same time, you'll be able to see a brown gas is evolved as a result of the reaction. So the completed reaction is actually showing here. And the initial reactants were copper and nitric acid, and our product is copper nitrate and nitrogen dioxide. So copper nitrate is ionic compound solution. The reason that we are observing a sky blue color comes from copper 2 plus ion, and the brown color gas uh, originated from nitrogen dioxide product. So now that we want to look at whether this reaction is really redox reaction or not, to be able to determine it, we have to determine the oxidation numbers of atoms in each substances. And copper case is 0, and the oxidation number of hydrogen is a +1, nitrogen is a +5, oxygen is -2. And in copper nitrate, the oxidation number of copper is +2. And nitrate, this is a polyatomic anion. You will be able to determine the oxidation number of oxygen is -2, and the nitrogen is a +5. And in NO2, the oxidation number of oxygen is -2. Then oxidation number of nitrogen is +4. And H2O is the same as before, +1 and -2. Now, when you look at the oxidation number change for the copper here, 0 to +2, so we can say that the copper was oxidized. On the other hand, when you look at the oxidation number change in nitrogen, starting from +5 to -2, so oxidation number has been reduced, right? So therefore, this is the reduction process. So apparently, this reaction is a redox reaction. Okay, now let's conduct the second experiment. First, you guys need to prepare a copper sulfate solution. So copper sulfate is an ionic compound, and it is very soluble in water. And the color of the solution shows sky blue color. Then after that, you can place a zinc metal strip in a copper sulfate solution. Later, you will be able to see the color of copper sulfate solution is getting clear. And when you look at the surface of a zinc metal strip, you'll observe the formation of brown granules, which is actually the copper metals that was formed from the reduction reaction. So what is happening here? We have a completed balanced reaction equation here. So zinc and copper sulfate is our reactant, and the zinc sulfate and copper are our products. Now that we want to determine the oxidation number for these substances, and the oxidation number of zinc is 0 in a zinc metal, and in zinc sulfate, the oxidation number of zinc would be +2. And in copper sulfate solution, the oxidation state or oxidation number of copper is +2. That is the charge of copper. And the copper metal, the oxidation number is 0. So what happens is that as copper 2 plus is reduced to copper metals, the concentration of copper 2 plus in aqueous solution is decreasing. So the color of copper sulfate solution is getting clear. And as copper 2 plus is reduced to copper, that is the brown granules formed on zinc metal strip surface. So as the time goes on, zinc metal strip size is going to shrink because zinc is eventually dissolved as zinc 2 plus ion. So when we look at the oxidation number change, zinc was apparently oxidized because its oxidation number was increased from 0 to +2, and copper was reduced by looking at the oxidation number decrease from +2 to 0. So apparently this reaction is also a redox reaction. In acid-base chemistry, we once did acid-base titration to determine unknown acid concentration. Similarly, we can use redox reaction to determine the unknown solution. So in this case, we have to have reducing reagent and oxidizing reagent to use the titration. In this specific example, the unknown solution is iron sulfate solution, and the standard solution is permanganate solution. So the concentration of permanganate solution is 0.1327 molar concentration, and it was placed in a burette. And 25 ml of unknown iron sulfate solution was placed in a flask. So you're going to slowly add the potassium permanganate solution, and at the near the end point, the solution color turned a pale pink color. So then you can read the burette volume. So in this case, we came to know that we added 16.42 mils of potassium permanganate solution was added to complete the titration. So what will be the concentration of the iron sulfate solution in molarity? So to determine the concentration of iron sulfate solution, we have to know the stoichiometric ratio between iron 2 plus and permanganate. So the reaction between iron and permanganate is apparently a redox reaction, and we need to know how to balance the redox reaction. This topic will be discussed in Chem 112. So we are just going to use the result of a balanced reaction equation. And as we can see here, 5 mole of iron 2 plus will react with 1 mole permanganate. So this is what we are going to use. As a side note, let's try to determine the oxidation number of each substances. And iron 2 plus case is that the oxidation number is +2. and Fe3 plus is a plus 3. And in permanganate, the oxidation number of manganese is plus 7, and Mn2 plus is plus 2. Now it is very clear Fe2 plus underwent oxidation. On the other hand, the permanganate was reduced during the chemical reaction. Okay, so first step, let's try to determine number of moles of permanganate that was added during the titration. So we have to start with the concentration of permanganate, which was 0.1367 molar concentration, and multiplied by the volume of the permanganate you added, which was 16.42 milliliter, and we needed to convert it in liter unit. So that's why we need this conversion factor. Then you can get the number of moles of permanganate, which was 0.002179 mole permanganate. Now, second step, what matters is how many moles of iron 2 plus was reacted with the permanganate. Now it is time to use a stoichiometric ratio, which was a 5:1 mole ratio. And we want to start with the permanganate, the number of moles of permanganate, and then followed by the conversion factor, which is a stoichiometric ratio between Fe2 plus and permanganate, which is 5:1. And you will be able to get the number of moles of Fe2 plus was 0.01089 mole. Then the final step is to use the definition of a molarity, and the molarity of Fe2 plus will be calculated by dividing a number of moles of Fe2 plus by the volume of Fe2 plus solution, which was 0.02500 liter. Then as a result, you will be able to determine the concentration of Fe2 plus was 0.4356 molar concentration. So this is the end of the redox chemistry. I hope you guys understood the topic very well.